Okay, so in the previous section, we have looked into the axioms and the various theorems of Boolean algebra that were required as prerequisites before we delve deeper into designing circuits using such concepts, right? So I'll just quickly go past the uh, kind of concepts that we have already covered. So please keep in mind that there are these equations. These are immensely useful when we try to design circuits, particularly so when we try to simplify circuits. For example, given a Boolean expression that we have already studied or seen at some Boolean expressions in the last class, yeah, it may have a circuit realization, but if you are able to simplify the Boolean expression using these theorems or axioms, you may be able to get a circuit realization that is way simpler, right? Which is going to save you the number of gates or the number of connections each gate can have, right? So you can do some kind of an optimization on the circuit design. So just to review, we are going to have these three basic Boolean algebra functions. One is this not or complement. Often it is read as a bar or not a. If a is 1, then a bar is 0 and vice versa. And when you write Boolean algebra expressions, it is typically written as a bar or a prime. And if you want to write it in terms of a circuit schematic or a gate level schematic, you use this triangular sign, right, with a circle in front, right? So the circle typically represents a complement, right? So if you do not have the circle, the output is going to be a. Often this is called a buffer. So if you do not have the small circle in front, if you input a, a is going to be repeated on the output. Okay, this is just for your knowledge. It is called a buffer. Okay, so similarly, if you have an AND operation, it is written as a dot b. That a and b has to be simultaneously true in order to be the output to be true. Okay, so this is shown as the shown on the right hand side as the truth table. So this is the truth table of the function. So you have the Boolean algebra expression, which is represented as dot. For or, you are using this plus sign, which means a or b, and for and it is a dot b. And these are the circuit level schematics. This rounded shape figure, right? It basically represents an AND gate, whereas this OR is represented on the bottom side, right? This is more like a more curved, right? More pointed. And what you need to know that either one or either A or B, one of them has to be 1 in order to make the output 1. Okay. So this is also evident from the truth table. If you see, if both of them are 0, the output is 0. If at least one of them, right? So this is at least one should be the value 1. So then the output is 1. Okay. So these were the three basic functions, and then we looked into the basic axioms. I'm not going to go over these slides. I'll just go past these things quickly because this has already been revised in the, like I introduced in the last class. So there are a few methods, or there are a few Boolean algebra, we call it axioms, and you need to know these to simplify, right? You need to at least sometimes recall this so that you can do some kind of a given a complicated expression, you can find out how to go further simplifying it. It will be easier for you if you remember these laws, right? So the distributive laws, identity, commutative laws, and so on. And we went past all these things, and then there was this concept of axiomatic duality, where we said that every Boolean expression has its own dual. Okay, so how do you construct a dual? And the dual, it's going to be equivalent, right? You can think of the dual expression as well as the original expression to be equivalent of each other. They are not going to be having any different kind of a behavior. but you could be using a different set of expressions or different set of operations in the dual expression compared to the original expression, and that could be required while you try to design hardware, right? For example, what do you do in creating a dual? This was like AND gates getting or AND operations getting replaced by OR operations, and vice versa, OR operation getting replaced by AND operation. And wherever you have constants like 1 or 0, which is like logic high or logic low, this is going to be again flipped, right? So constant 1 is going to be replaced by constant 0, and constant 0 is going to be replaced by constant 1. What you really need to remember if you want to find out a dual is that you cannot change complements, right? For example, if you have a bar, you cannot change it to a. So this is not allowed. This is not allowed. So you need to keep the expressions that has this complement sign like a bar or b bar, whatever be the case, those intact, right? You cannot touch them, but you can change the ands to ors, and constants you can flip the value. Okay, and the good part here is that often you may require an expression that has more number of ands compared to ors, or more number of ors compared to ands. This is the thing that you can apply, and the reason I was telling you that you need more ands than ors or more ors than ands is directly related to how you design the hardware. So in your hardware you might be using more, you might be favoring to use more AND gates because of whatever reasons. It could be cheaper, it could be easily available to you, right? That will give you a flexibility in the design choice. Okay, so you need to understand why this duality is important. This is apart from a mathematical construct. You need to understand that this duality has a valid use in hardware design. Okay, so examples I have given, you can just revise this, you can or come up with some of your so take some Boolean algebra expression and try to find out its dual, and maybe draw the truth table for these two functions and verify that they are indeed equivalent. Okay, so this exercise is really going to help you. And we again looked at the dual expressions for all the axioms that we have studied, right? And there were some simplification theorem, and we also went through them. If you want to do simplification yourself of some Boolean expressions that are somewhat complicated, right? You should be using these laws. So we did a simple demonstration. These were not very complicated expressions, but we will be also giving you tutorials on how to solve or how to simplify a little bit more complex Boolean expressions, and you could be using these laws like distributive laws or commutative laws and other axioms to simplify them, right? So this is also going to give you some practice, and always try to remember that again we are going to cover those grounds today. All the exercise that we have been doing in this context is not really just for the fun of solving some algebra problems, but they are connected to actually building computing systems, right? We will very soon try to create a correspondence in between these algebraic expressions that you are trying to build to an actual circuit that you can physically look and feel, right? So if you remember, we gave you an example of the tic-tac-toe game, right? So in the tic-tac-toe game, we had 9 inputs and we wanted to know whether a particular user is winning or not, right? So we are trying to tell you that this entire concept could be abstracted out in terms of Boolean algebra. You can make necessary mathematical operations on those expressions or on the truth tables. You can simplify them and so on. And at the end of the day, you are going to take the finalized expression and convert that into an hardware circuit. Okay, so that is the motivation behind going through this material. Okay, so this was about the some proving, right? You need to do some kind of take algebraic expressions, use the existing axioms and try to prove or try to simplify things. Okay, And the last but not the least, which is really important, is the De Morgan's law. So the De Morgan's law is basically, if you have an OR of these variables or literals, right? We are going to come into those definitions later. This x, y, z, and so on, right? So these are all Boolean variables, right? It can take the value 0 or 1 if you have them, and you take a bar, right? So you try to do a complement of this entire expression containing all these n different elements or together. This is equivalent to individually complementing them, right? Individually complementing these literals and doing an AND. Okay. So again, as you can see, this is almost like your dual, right? So you do not really change the complement here, right? So what we were trying to do is we do not touch the complement if you try to find out the dual. But in this case, this is a particular law called De Morgan's law, where this entire expression of the complement sign over the entire expression could be broken up into like complementing individual values and replace the OR operation by an AND operation. This is a very important result for simplifying Boolean algebra expressions. Okay, so you'll come across this thing very frequently. So I also gave you the kind of a physical interpretation, or like more of a logical, like verbal interpretation, right? Not the math being involved. Was that if you have this expression called f is equal to a plus b plus c, if you just apply De Morgan's law, this becomes a bar dot, like, and b bar and c bar, right? And if you think of kind of arguing, right, with using simple common sense or logic, right, this expression could be said something like this, right? So on the left hand side, we have f, right, which is written as a plus b plus c, right? So a plus b plus c could be thought of a statement which says that at least one of a, b, or c is true, right? Because I'm basically saying f is equal to a plus b plus c. Doesn't matter how many of them are ones, as long as you do not have all zeros. The rest of the cases are going to be ending up as f is equal to 1, because at least one of them will be 1. Okay, so we want to see there is a if you apply De Morgan's law on the right hand side, like the right hand side expression becomes a bar dot b bar dot c bar, and both sides we have this top bar, right? So if you follow the slides here, so we write f is equal to a plus b plus c double bar. So bar of bar means it is complement of complement, which is basically the same thing, right? So we try to just write this expression to create a similarity or apply De Morgan's law. So we basically take the lower bar, right, and then apply De Morgan's law to it, and this becomes a bar dot c bar dot b bar dot c bar, right? So here we again verbally kind of infer the statement, right, which logically says that it is not the case that a, b, and c are all false, right? So we say at least one of a, b, and c is true, right? At least a, b, one of a, b, and c is true, which basically means that it is not the case that they are all false, right, or all not true. Okay, simultaneously. So you can think about it, and this basically gives you an insight, actual physical insight into why this De Morgan's law works, right? You should not be just given this expression and you are asked to believe this expression is true. Of course, mathematically using truth tables you can verify that, but sometimes that will not give you a logical satisfaction, right? That why these two expressions are equivalent. Often using such statements you would be able to reason to why this has to be true. Okay, so I would encourage you to even for all Boolean algebra expressions, in fact you can actually come up with these statements, right, and then just for fun, you can try to see that you can take two such expressions and try to compare these statements, right? They have to be the same. Okay, they have to be the equivalent at least. Okay, so that was the primer on the Boolean algebra expressions and axioms and duality, De Morgan's law, and so on. So now we are going to delve a little bit deeper into using this to create logical circuits. That's the next step that actually follows from what we have studied so far. Okay, so uh, now let us kind of pose what exactly, again going back to the transformation hierarchy and trying to give you the future plan, right, or the roadmap of what we are going to do next. So again, we come back to our favorite transformation hierarchy or higher levels of abstraction. I will try to remind you that we are again going to focus on the design of these digital logic circuits, along with kind of using such circuits to create the microarchitecture of a very simple computer, or we are going to create some kind of a simple CPU processor and so on. Okay, so till now we have looked into things like Boolean algebra and logic gates. You might ignore this part, but just to summarize, this is something which basically starts before logic gates. Rather, this has something to deal with the circuits part, where we try to show that, or even the devices part, where we try to use transistors as the basic building blocks to create a gate, right? So if you remember, the very first figure that we had was trying to disintegrate a Google Pixel phone, right? It kind of disintegrated into some PCBs. Those PCBs had internal ICs, and these ICs had modules. The modules had things like cells, and each cell was made of a few gates, right? And those gates were actually made of transistors. So if I ask you that this is a NOT gate or an AND gate, the AND gate itself, right, is not a physical reality, right? This is more of a logical expression. If you put two high voltages, right, let's say, just to summarize this part, right, and also to kind of give you more clarity on what these hardware circuits are. Let's say there is something like an AND gate. This is not a physical reality. There is nothing like an AND gate that exists, right, that is going to do this Boolean algebraic that has this Boolean algebraic properties, that given these two digital inputs A and B, it is going to follow the logical output A dot B, right? So this logic is actually implemented, right, using a system of transistors, and we are not going to go into the details of how it is done, but for the sake of your knowledge, you should know that this AND gate or an OR gate, this is a schematic, right? So you take this collection of these transistors, which is typically called a transistor network, and try to create this gate, and we basically give a level for us to understand, right? It is for your diagrams or schematics, right? So people can easily identify that the circuits, this logical block is an AND gate, right? It is kind of improves your readability, or eases you. It's easy for you to communicate this circuit diagrams to your colleagues and so on. Okay, so that is why this was a starting point, but we will not go into these details given the flavor of this particular course that you are a part of. So it starts from transistors. We build logic using those transistors. We create logic gates. So currently you are aware of various gates like NOT gate, AND gate, OR gate. At the same time, you can have XOR, right? We did look into these things like XOR, XNOR, and so on, but we are going to touch upon them more. And we also looked into things like Boolean algebra. So all the axioms and laws and so on, right? Logic simplification, duality, and so on. So we also showed you a picture, right, where this could also the logic gates, right, or the Boolean algebra, and they can be actually combined together to create these circuits, right? So now we will look into the fact that how can you create certain class of circuits, right, or certain class of logic which is called combinational logic. So the combinational logic, if you remember, we spoke of two different kinds of logic. One was the memoryless logic, which is combinational, and the other one was retaining something from previous states, right? So it's a function, the way the circuit behaves, it actually carries forward the state of the circuit with time. So what you get next is a function of the current inputs as well as what you had earlier. That those are called sequential circuits or sequential logic. So the combinational logic that we are going to look into now is purely a combination or a function of the current input. So I'll write CL for combinational logic. This is purely a function of the current inputs. Okay, so whatever you give to the circuit currently right now, you will get those as outputs as specified by the functional specification, right? It should have a truth table, and the truth table tells you the functional specification means how the inputs get mapped to the output. Okay, and remember, this is memoryless. The word memoryless here is used because it does not retain any information from the state when previous set of inputs was given. So think of an adder circuit. If you try to add 4 and 2, the output is 6, right? The next time you want to add 2 and 7, the output is 9, right? So 4 plus 2, 6, and 7 plus 2, 9. These two computations are completely independent of each other. Okay, so when you compute 7 plus 2 is equal to 9, in no way the previous output, which was 6, or the previous inputs, which was 4 and 2, is going to interfere with the current state of computation, okay, or the current state of execution of the circuit. So it is typically only the current inputs, and it is, you can think of this as a memoryless circuit, okay, or logic. So that is primarily about the combinational logic. We are going to look into many examples of combinational logic blocks and how they form an integral part of the modern computer, right? If you want to design a computing unit or a processor, there's a lot of this combinational logic blocks that has to be used in order to create such a system. Okay, the next thing that we are going to cover is the how do you minimize such combinational logic circuits. So while I was discussing about Boolean algebra, if you remember, I was referring so many times about simplification of these Boolean algebra expressions. Okay, so given a circuit or given a huge truth table, right, that gives you the functional specification of the circuit, one idea is to simply just convert that into some kind of a logical expression and build a circuit for it, right? However, there might be room for improvement to minimize the cost of the circuit or to reduce the like form factor of the circuit by using lesser number of gates. So what we are going to study is that there are some formal ways of minimizing such combinational logic circuits or expressions. So one way is to use the axioms that you have already studied. You can use them and let's say make your life easier, right? So you can make simpler versions of this circuit. There will also teach you some formal methods. Sometimes you need to use a lot of these tricks, right, to figure out the simpler expression. But suppose there are some like solid techniques, right, where you don't have to really do a lot of algebraic manipulation, but this is more of a mechanical way to sort of take you towards an optimal design. Okay, so we'll study this minimization of combinational circuits. You can think of the one-liner for this is, given a complicated expression, we are going to teach you a very mechanical solid way which is going to convert a complicated expression to a more simpler version if possible. Not all the expressions could be further simplified, right? Uh, then we'll also look into this common combinational logic blocks. We are going to talk about it anyway, not separately, together, right, in this entire course of lectures. Various kinds of combinational logic blocks that are going to be actually used to organize the CPU design, right? How do you create the basic organization of a arithmetical or logical unit, or how do you kind of use these various kinds of combinational logic block elements to refer to various segments of the memory and so on, right? So this will be very, very important. Okay, so in this course of few lectures that we are going to go from now on, this will primarily, we will focus on design aspects. So given a problem, how can you come up with a combinational logic circuit for that particular problem, right? That is the main outcome, the learning outcome. If you want to talk about, this should improve your skills to come up with a combinational logic circuit for the same problem. Okay, so from now we will come up with the definition of a few things. So for example, the first thing that we would start with is a sum of product expression. So before going into that particular terminology, let us say that, assume that you have this truth table of a Boolean function. So this is a standard way to represent that truth table in a different form. Okay, these are all various forms. For example, when you studied chemistry, right, you had so many forms, right? For example, you may say it's water, or you can say this is H2O, right? Or carbon dioxide is one way to write it, right? CO2 is another symbolic way to write it. Similarly, or even for organic things can become very, very complex, right? Either you can draw the molecular structure, or you can write the UPAC name and so on, right? So here also there are several alternatives. Okay, so one is a truth table. As you have seen in the tic-tac-toe example, the number of rows in the truth table goes on exponentially increasing with the number of input variables. So we had 9 inputs, right, in the tic-tac-toe table, right? If you remember the tic-tac-toe example, we had things starting from A11, if I remember correctly. There was A33, A11, A12, A13, A21, like that, and you had an output, right? So the number of possible input rows that we can have can run to as much as 512, which is nothing but 2 to the power 9. Okay, and you cannot really not a very compact way to represent this, right? You have so many different entries in this particular table, which makes manipulation or communication of this particular thing very cumbersome. Okay, so there are other ways. One of them is called the sum of products. Okay, so we express the truth table as a two-level Boolean expression. Okay, why two-level? We are coming to that. But remember, this is a very standard way to represent any truth table. Okay, so we want to first see that the expression that contains all input variable combinations, which is resulting in an output of 1. Okay, so this is very important. First thing that you should do, you should look at the truth table. Immediately you don't have to look at, or you can start ignoring rows that has an output of 0. Okay, you should only consider rows that has an output of 1. That is the first level of filtering that you can use. So you don't have to write the remaining rows because they are anyway redundant, right? Why? Because if you know the output is 1, the other output has to be 0, because this is a Boolean or binary digital kind of an expression or circuits that we are trying to build. So there are only 2 states possible. It could, if it is not 1, it has to be 0. If it is not 0, it has to be 1. So instead of picking up zeros, now we are picking up only ones, and anybody can say that the rest of the input combination leads to a 0. So if any of the combinations of the input variables that result in 1 is true, then the output is 1, right? So the first bullet says that we should be concentrating on the rows. We should be concentrating on the rows that result in a 1. The next bullet statement says that if any one of the rows are true, right? Because two rows cannot simultaneously happen, right? Because every row indicates a unique input, right? So for example, if I give you a simpler way or a simpler less complicated truth table, let's say you have these three inputs, let's say x1, x2, x3, and you have some kind of an output. Okay, so what we are trying to say, we first select rows. Let's say you have a 1 here for some inputs and you have a 1 here for some inputs, and the rest are 0. Let's say this input is 1 0 1 and let's say this input is 1 1 1, right? So what we are trying to say is we are going to pick up rows that end up in a 1 in an output, and then we are also saying that any of the input combination that results in a 1, which is basically either this or this, will result in result in 1, right? So basically it's a logical OR of this kind of input combinations or this input combination. Okay, so this is the reason we are talking about a two-level thing, right? So your function is a OR of all the input variable combinations that result in a 1. Okay, it's as simple as that. So, but it's a very useful way to represent truth tables, and it's a standard way, and you will also appreciate the benefits of using the sum of the products expression. Okay, there are many other techniques that will take the standard sum of the products as input and then try to simplify them. Okay, so here if you think of this particular case, so the first the one is basically x1 and x2 bar, right? x2 complement and x3, right? So this is one input combination which makes an output is equal to 1, or this is another input combination which is x1, x2, x3, right? You have a dot, right? Sometimes we forget to write the dot, but this is assumed to be an AND operation. Okay, so this is like the first expression, if it is true, the output is 1, or if the second expression is true, the output is also 1. That is the essence of what we are trying to say in this particular case, right? So just to interpret the physical structure of this expression, it's a sum of products. Okay, so every such input, if you think, is actually represented as a product. x1, x2, x3, x1, x2 bar, x3. It could be any other things like x1 bar, x2 bar, x3, right? Which is like 0, 0, 1. Okay, given that x3 or like without bar, we represent that to indicate 1. Bar is 0, so x1 bar, x2 bar, x3 could be 0, 0, 1. But remember that, or observe that this is basically in the product form. Okay, and what we are trying to say is that the final output is going to be a sum of the product. You might have three inputs, right? Maybe here let's say 0 1 0. Okay, this also led to 1. Okay, so you have another one plus what will be 0 1 0, x1 bar, x2, x3 bar. Okay, so this is a sum of these products.